All right. So 6.3 part 2. All right. We said yesterday that a unit vector u has magnitude equal to 1. So in symbols we would say the magnitude of u is 1. We can think of a unit vector as a pure direction. We're not worried about the length, we're worried about which direction it points. So a unit vector is kind of a vector with pure direction. And often we're interested in the direction more than the magnitude. So if we have a vector v that doesn't have a magnitude 1, well, we can find a unit vector in that same direction what we're doing is that we're essentially, what we want to do is divide out the vector's magnitude. Just like if we divide 5 by 5, we get 1. So we're going to divide the vector by its magnitude. And the way we write that is 1 over the magnitude of v times v, or the way I usually write it is v over the magnitude of v. So we're just dividing away its magnitude. And the reason that we might want to do this is because all we're interested in is the direction. So we want to figure out the direction. We want to do something in the same direction, but we want the magnitude to be 1, so we can then adjust the magnitude to what we want it to be. So we're interested just in the direction. So for example, if we want to find the unit vector in the direction of vector v equals 3, is that the one I want to use? 3, negative 4. Well, this vector doesn't have magnitude 1. So we're going to find a vector that does. So we're going to find the magnitude of v. It's going to be the square root of 3 squared plus negative 4 squared. And if we think of 3 and negative 4 as two sides of a little right triangle, what's the hypotenuse? 5. So a unit vector is 1/5 of 3, negative 4. So I can also write that as 3/5 comma negative 4/5. And that vector is going to have magnitude 1. So let's check. The magnitude of u is the square root of 3/5 squared plus negative 4/5 squared, which is the square root of 9/25 plus 16/25, which is 25/25, which is 1. So we divide it by its length, and that makes the new vector have magnitude 1. Now what if, so I'm going to call this part 1. What if part 2 says find a vector with magnitude 15 in the direction of V. What would we do? Yeah?
Just multiply our new vector by 15.
Multiply our unit vector by 15. Our unit vector is in the direction, points in the direction of V. It has magnitude 1. We want our new vector to have magnitude 15, so we can say our new vector is 15 times 3/5 negative 4/5. And we could also write that as 5 divided by, or 15 divided by 5 is 3. So that would be 9, comma, negative 12. And the magnitude of this vector would be 15. And it's in the same direction as V. Because if we check the slope, negative 4/3 is the same as negative 12/9. Their slopes are the same. They have the same direction. Yeah.
So would it be possible to like figure out, to graph that using the component form?
Yeah.
Yeah.
Mm-hmm. All right. So now that we know a little bit about unit vectors, we often use, more in science than in math, we use standard unit vectors. So our standard unit vectors in 2 dimensions are I hat. This is the vector 1, comma 0. And j hat is the vector 0, comma 1. And the way we can think of these is I hat is just a unit vector that points in the x direction. And j hat is a unit vector that points in the y direction. And if we have V in component form, V1, comma V2, we can say in terms of the standard unit vectors, V1 is V1, vector V is V1 I hat plus V2 j hat. Just a different way of writing vector V in terms of the standard unit vectors. They mean the same thing. I hat means you go in the x direction, j hat means you go in the y direction. We call this a linear combination of the standard unit vectors. And second semester, when we learn about 3-dimensional vectors, I'll be able to show you one of my favorite vector jokes. I'm already looking forward to the vector jokes. But most of them are about 3-dimensional vectors. So, for example, the question you might be asked along these lines is write 3, negative 4 as a linear combination of the standard unit vectors. And what that means is we can write 3, negative 4 equals 3 I hat minus 4 j hat. Those two notations mean exactly the same thing. This is kind of standard mathematical notation. This is more what you would see in a science class, in physics class. But they mean the same thing. Yeah.
So is that a variable or is that a different way to write it?
It's a different way to write it. I hat just means in the x direction, j hat means in the y direction. Yeah, the two notations mean exactly the same thing. All right. I've been promising that we would bring trigonometry back into what we're talking about with vectors. And we've been missing trigonometry for a couple of days. So let's bring that back in. So we'll talk about direction angles. And what we're talking about today really, or what we're talking about here with direction angles really isn't anything new. This is going to be exactly what we did when we talked about, when we first started talking about trigonometry. So I'm going to draw a set of coordinate axes. So there's x, y, and I'll put a vector on there, make it a blue vector. And I'm going to call that vector v. And we're going to talk about this angle that the vector makes with the positive x-axis. So our vector is in standard position. This is the origin. And what we're going to do is draw a little right triangle here. If the magnitude of v is 1, so that's like saying that the hypotenuse is 1, kind of like saying we're on the unit circle. Not kind of, exactly like saying we're on the unit circle. This x, so I'm going to say this is at a, b. If the magnitude of v is 1, a is just cosine theta. The x-coordinate is the cosine of the angle, and b equals sine theta. We can write then that v in component form is cosine theta sine theta. And that's the same as saying cosine theta I hat plus sine theta j hat. So we can talk about the vector in terms of the angle it makes with the positive x-axis. If the magnitude of v is not 1, so I'm going to draw a new set of axes and a new vector. Oops. And we're still in standard position here. There's y. And I'll do this vector green since its magnitude isn't 1. And it's still, the terminal point is still at AB. We're going to draw a right triangle here. And this is still at the origin. Well, in this case, A is the magnitude of V times the cosine of theta. We're using the Pythagorean theorem here. This is adjacent hypotenuse. And B is the magnitude of V times the sine of theta. The magnitude of V is the hypotenuse of that triangle. And we can write that V then, in component form, is magnitude of V cosine theta, comma, magnitude of V sine theta. So all we need to know about the vector in this case is its magnitude and the direction it makes, the angle that it makes with the positive x-axis. And this is the same as writing the magnitude of V cosine theta I hat plus the magnitude of V sine theta j hat. Component form and in terms of the standard unit vectors. Because often it's convenient to talk about vectors in terms of the angle that it makes with the positive x-axis. For example, if you're firing some kind of projectile, a cannon, and it makes a certain angle with the vertical, or sorry, with the horizontal, with the ground. So you want to talk about the path of the cannonball based on its speed and the angle that you fire it from the angle it makes with the ground. All right, does this make everybody feel good? We got our old friend trigonometry back. It's like that. Did I told you about that shirt that I saw the one time, right? I was a day without trigonometry is like a day without sunshine. Said a day without math is like, oh, never mind, I have no idea. Kind of the same thing. Yeah. All right. So examples of problems that you might see that involve that idea. We want to write V in component form. If the magnitude of V is 25 and V makes a 38-degree angle with the positive x-axis. Well, this is easy. This should be a gimme if you see a problem like this. This is just saying V equals 25 cosine 38, comma 25 sine 38. If it asks you to write V in terms of the standard unit vectors as a linear combination of standard unit vectors, 25 cosine 38 I hat, that should be a 5 there, plus 25 sine 38 j hat. We can multiply that out, put it in your calculator, but that's fine. This component form, this is in terms of, or is a linear combination of the standard unit vectors. Yeah.
Do you have to multiply those out?
I would, you could leave it like that. The problem might ask you to round to the 10th or something. I'm fine with it the way it is. Yeah.
If you do multiply them out, you would still leave them as like your number I have plus
Mm-hmm.
another number.
Mm-hmm. Yeah, you just get a number here and a number here. Yeah. Just like you'd get a number here and a number here. Your x and your y. We might also be asked to go the other way and find the direction angle. Of V equals 2 I hat minus j hat. And I think, let me go back here. I think I forgot one thing. We know this from when we talked about trigonometry, but tangent theta is opposite over adjacent, so it would be B over A. Y over X. That's what we talked about before. All right, so there's our direction, there's our vector. Well, we know that, well, first off, what quadrant does that vector point into? Fourth, right? 2 in the x direction, 1 in the y direction, negative 1 in the y direction. So there's our vector, and the angle that we're interested in standard position is that angle. So we need a fourth quadrant angle. So I'm going to say tangent theta is -1/2. So theta is the inverse tangent of negative 1/2. And my calculator says, oh, the domain restriction on the tangent function for it to have an inverse is negative pi over 2 to pi over 2. So it's going to give you negative 26.57. Well, we want that angle in standard position from the positive x, counterclockwise from the positive x-axis. So what do we do? Subtract from 360. Theta equals 360 minus 26.57 equals 333.4 in standard position. So there's our fourth quadrant angle in standard position. Mm-hmm.
Where did you get the negative 1/2 from?
Negative y over x, negative b over a. And if I think about this little triangle, this side is 2, and that side's negative 1. So the tangent is opposite over adjacent. All right, other questions there? Okay, one of the main applications of vectors that we'll see, you'll see others, is static equilibrium. So we'll get some kind of situation, some kind of problem set up that looks something like this. So we have these pulleys. And we have some kind of weight that's suspended on cables from these pulleys. I have no idea why you'd want to suspend a load from pulleys in this orientation, but this is the kind of situation we're going to set up. So we've got this 5,000-pound weight hanging from these cables. And I'm going to say that this angle is 60 degrees, and this angle is 50 degrees. And we have some tension in this cable. I'm going to call that T1. And some tension in that part of the cable, I'll call that T2. And what we want to do is find T1 and T2. So what we're going to do is think about the tension in this cable, the force that it's applying, as a vector. So that one's pulling up that way, that one's pulling up that way. And we're going to break the vector into parts that are vertical and parts that are horizontal. And with static equilibrium, the key is the vertical portions has to support the weight. So whatever the vertical portions of the tension are, they have to, that's what's supporting the weight. The part that goes up and down, supporting the weight. The horizontal components because this thing isn't moving side to side, that's what static means, that's what equilibrium means. It's not moving side to side. The two horizontal pieces have to equal each other. Otherwise it would be moving. So what we're doing is visualizing. I'm going to draw two little pictures here. So I'm going to break this into two triangles like so. So this is a 60-degree angle. And we have the other portion. I'm just thinking of it in two pieces, like this. And that's a 50-degree angle. And this is T1. And this is T2. There's my vector pointing up that way. Well, this vector is made up of two vectors that go sideways and up. That one goes up and sideways. And what we're going to do is use a little bit of trigonometry to figure out these vertical pieces and the horizontal pieces. Well, on the left triangle, this side of the triangle is T1 cosine 60 degrees. This is the adjacent, and this is the hypotenuse. This one is T2 cosine 50 degrees. The side-to-side pieces have to equal each other because it's not moving one direction or the other. So I'm going to say T1 cosine 60 equals T2 cosine 50.
Hey, Beamer.
Hello.
Is Evan here? There you are. Can I interview him? This with me?
Sure.
Thank you. Oh, hey, Eric.
Hey,
What happened to your nose?
Russians.
Oh.
On the left triangle, this vertical piece is T1 sine 50. It's the opposite and the hypotenuse. And this vertical piece on the right triangle is T2, sorry, this should be a 60. T2 sine 60. Well, those together are what are the forces that are supporting the weight. So T1 sine 60 plus T2 sine, I keep getting my angles mixed up. This should be sine 50. There we go. That's good. And T2 sine 50 equals 5,000. Those vertical pieces added together are what's supporting the weight. Well, now we're going to plug some numbers in. So for that top equation, cosine of 60 is 0.5. So these are my equations. Do we see what we're going to have to do here? We have two equations with two variables. Going to have to either use substitution or elimination. I'm going to suggest substitution. So 0.5 T1 equals cosine of 50 is 0.64. 0.64 T2. And then from this one, 0.866, sine of 60 is 0.866, square root of 3 over 2, about 0.866. T1 plus sine of 50 is 0.766. That equals 5,000. So this is my system of equations. From the first equation, I get that T1, divide both sides by 0.5, is 1.28 T2. And what I'm going to do is take this and substitute it right there. So 0.866 times 1.28 T2 plus 0.766 T2 equals 5,000. Well, I can combine these together. I'm calculating on the fly here. Times 1.28. So I get 1.11 about plus 0.766 T2 equals 5,000. Add these two together. And I get about 1.87. T2 equals 5,000. Divide by 1.87. And I get that T2 is 2673.77 pounds. And then from this, I can multiply it by 1.28 and get T1. And I get T1 is 3422.46 pounds. Yeah.
Could you also subtract the 2673 from the 5,000, or would that not give you the right answer?
That would not give you the right answer. Yeah.
So when you're saying like T1 and T2 come out as this weight, is that like the weight of the cable or the?
No, that's the force in the cable. So the cable is exerting 2,673 pounds in that direction. That's the force that that cable is exerting on the weight. This other cable is supporting, or has 3,422 pounds of force in it. It's applying that much force to the weight. Why do those two add up to more than 5,000?
Because wouldn't it, if it added to 5,000, that mean it was rated that much?
Well, so 5,000 pounds of force is what it takes to support the weight. The other part is what's keeping the cables from moving, because they're at an angle. It's what's keeping them from moving from side to side. So you have 5,000 that has to support the weight. You have some more force that is keeping the cables from going side to side. So that's why it doesn't add up to 5,000. It's more than 5,000. Yeah.
So can we determine the amount of force using that, like for each side? Do we need to do that, or is it kind of like does that make sense? So if it goes over 5,000, do we need to determine like is there going to be a problem that we need to determine how much extra force?
No.
Okay.
The problem might ask you if your cable is rated to 6,000 pounds, is that going to be a strong enough cable to support the weight in this situation? Then you could look at these two and say, well, it's a little more than 6,000. No, it's I mean, would it be 6,000? Yeah, it would be a little more than 6,000.
So it would be yes.
So if the cable was only rated to 6,000 pounds, then it wouldn't be strong enough, because we have over 6,000 pounds of force being generated in that cable.
Okay.
All right, questions? Okay. And those last three, 97, 98, and 100, are essentially like the problem that we just did with different numbers. So the setup, the solution method is really the same.